Alright, welcome to Unit 2 of differential equations. So, in the first unit, we went over first order differential equations, which are just differential equations with only one derivative in it. So, if it was Unit 1, we'd have something like this. But now, we have a second derivative in the mix also. And we're going to start this. This whole section is how to solve these second order differential equations. And to start, we're just going to be worried about homogeneous ones with constant coefficients. So it being homogeneous means it equals 0. If this was like something like a d, some constant d, then it would be non-homogeneous. But to start, we're just going to be worrying about when this equals 0 and when a, b, and c are constants. Now we can solve equations that are like x squared times this derivative, x cubed times that, or like 2x times here, but we're going to build our way up to that. But for right now, we're going to assume that all equations we get will have second derivative, first derivative, just no derivative, all times a constant coefficient. So let's jump right into this. We're not going to be going over like specific examples. This is just a overview of what's to come. So there are three cases where they're called distinct roots. That's one. There's repeated roots. That's two. And then there's complex roots, which is three. And how we find out which one of these we use, we're actually going to try and factor this equation kind of like a polynomial. Just treat this second derivative as like x squared, this as just x, and then this is just like c. And well, we're going to have like the constant a, and then r is our roots, so ar squared plus br plus c equals 0. And sometimes you can just factor it, sometimes you may need to use the quadratic formula. But this is a little easier if we do an example. I know I said we weren't going to do an example, but we're not going to do the whole thing through. But let's say it's like y double prime plus 11y prime plus 24 y equals 0. Well, here a is just 1, so 1 times r squared plus 11r plus 24. And we can factor this out, just 3 times 8. 3 plus 8 equals 11, so we can get r squared plus 3r plus 8r plus 24, r times r plus 3 plus 8 times r plus 3, and we end up with r plus 8 times r plus 3 equals 0, so r equals negative 8 and r equals negative 3. So what's to point out is we get two different answers, thus distinct roots. If r equaled negative 3 twice, or negative 8 twice, it would be repeated roots. And if we got some imaginary result, we would have complex roots. So let's get into like the equations. And the sad part is we kind of just need to memorize these. They're not too hard to memorize, but they're not the easiest either. So for the first case, we get y of x equals c1, which is just a constant, times e to the r1 times x. And this can be r1, r2. Now, repeated roots is when r1 equals r2. Distinct roots is when they're different. And we just get c to e to the r2 times x. So that's our first case, where the roots are different. But let's say they both equal negative 3. Well, in that case, r1 equals r2. So we can just say it's r. And for this case, the equation's almost the same, but a tiny bit different. So c1 e to r times x. You can just say like r1 and r2, but they're the same. So it'd be redundant, so it would just say r. Plus c2 times x times e to the r times x. Now, I wish I knew the proof to these equations, because I'm sure they're like very satisfying, but I'm just not sure how to do them. And if you learned them, you'd probably like forget them pretty quickly. But let's move on to our last one, where our roots are complex. And in this case, we get e to the alpha x times c1 cosine of beta x plus c2 times e sine to the beta x. Now, what is alpha and what is beta? Well, let's I'll show you with a quick little factoring example. So let me just refer to my notes real quick. Just 1 second. Let's say we got something like y double prime plus 8y prime plus 20y equals 0. So we end up factoring this, and we notice that there's no real like way to multiply two numbers together that add up to 8. So we're going to use the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. And this works out to be negative 8 plus or minus the square root of 64 minus 80, and that is the square root of negative 16. So negative 8 plus or minus the square root of negative 16 over 2 equals negative 8 plus or minus 4i over 2 equals negative 4 plus or minus 2i. And, well, negative 4 is alpha, and 2 is beta. So the form is, when you factor it, alpha plus or minus beta I. And alpha and beta is what you plug into here. And notice how, despite getting a complex root, there's no complex things in this equation. So we can get a real answer, which is why this is so powerful. But in the next video, we're just going to be going over distinct roots, but we're then going to do repeated, then complex. And it's just a lot of practice for this. All you have to do is just grind out example after example, and you'll just memorize the equations naturally. And the process for all of them is the same. You'll have your equation, some initial conditions, you'll factor out the roots, decide which case to use, write that formula. You may need to derive the formula to find y prime if you have two initial conditions. Then you use those initial conditions to find the constants for your specific solution. But that's pretty much all I have for you now. I'll see you in the next video.